The objective of this video is to construct and solve complete magnetic equivalent circuits. We've been spending a considerable amount of time developing magnetic equivalent circuit elements for coils and steel regions as well as permanent magnets. In this video, we're going to consider connecting our various elements together to form a complete reluctance network, solving the reluctance network, and then using that solution to calculate our various field quantities. So to review, here are our fundamental elements. We talked about flux tubes within a continuous material, and these can be in any arbitrary shape. I've drawn it as a cylinder here, and these flux tubes translate to reluctance elements. We've also talked about coils, and in this case I've drawn a coil wrapped around a piece of material, presumably a piece of iron, and shown how that corresponds to a reluctance element in series with a source term, with current linkage. And our third type is a permanent magnet. And so we had two options for the equivalent circuit for the permanent magnet. We can either put it in its Norton form or its Thevenin form. So let's now consider a couple example structures that link these components together. So we've drawn a steel core here that extends axially into the page. So I've tried to draw the extent going into the page. And I'm now going to put a series of dimensions on it. And you can see that the key features of this core is that it's got a coil wrapped around one side of it, and it has an air gap over here. And so what we're going to do is sketch the magnetic equivalent circuit of this after I've labeled the dimensions. I've indicated the dimensions on here to give you a reason for assigning different reluctances or different flux tubes to different parts. So you can see that the height in the y direction is Ly along the side core here, whereas we have shorter cores going to the left and right, and then again going top to bottom above and below our air gap. And then finally we've got this air gap of distance delta. So please go ahead. Try to sketch a circuit, pause the video, and press play when you are ready to watch me draw the circuit. Alright, starting on the left side, we've got this coil, and the coil looks like a current linkage source or an MMF source. We're going to assume that the coil has N turns, so the current linkage is N times I. And this whole branch on the left side, it looks like a long reluctance, a long flux tube. And so we'll label that as this. And then going left to right on the top, going up here, we see that we have another flux tube. Coming down here, connected to the node of the top flux tube, we have a short flux tube going in the y direction. And then we've got our air gap flux tube, our air gap reluctance, and then another short flux tube in the y direction, and then our return flux tube. So your equivalent circuit should look like this. You can simplify this circuit by realizing that all these reluctances are in series and then just drawing this as a single MMF source and a reluctance. But for our purposes here, let's keep these all as distinct reluctances. And in part 2, I'd like you to write out expressions calculating each of the reluctances. And you can assume that the permeability of our iron is mu Fe, and the permeability in our air gap is air, so it's just mu naught. Press pause and press play when you are ready to watch me write out expressions. So I've written out an expression for our vertical reluctance, and the way that I've labeled the dimensions on here is actually to give you the dimensions of the flux paths. So Ly is the dimension of that flux tube. This is an approximation, because clearly our actual flux path will vary between going sharply around this corner versus taking a longer path out here. But we're going to approximate it on the green contour. At this point, we've been writing the expression for each of the reluctances in terms of the cross-sectional area of the flux tube A. And all these expressions assume the same cross-sectional area. However, in reality, the effective cross-sectional area of your air gap region is going to be different. That's because you're going to have some flux that's going to take a path kind of like this. It's going to fringe outwards. And there's different ways to account for this, but I'm going to modify the problem statement now. I'm going to tell you to assume the following. I'm telling you to assume that all of the iron regions have flux tubes with a cross-sectional area of A, but the air gap has an effective cross-sectional area of 1.5 A. And again, that's just an assumption that we're making in this one individual problem. Whether it's a valid assumption for an arbitrary geometry depends on what that geometry looks like. But in this case, we're going to just assume that. And so what this does is it changes your expression for the reluctance of your air gap flux tube to be the following. Part 3, we'll calculate phi. And this is pretty easy to do from our equivalent circuit. Phi is simply going to be our current linkage divided by the sum of our reluctances. And in part 4, I want you to calculate B core and B delta. So that is, find the magnetic field in the core cross-section and in the air gap cross-section. Press pause now and press play when you're ready to resume. And you can see we've got the following expressions for our field in our core flux tubes and our field in our air gap flux tubes. And since the assumptions that we made here is that the same flux flows through all parts of the circuit, that was our assumption about there being no leakage, flux flows where we want it to flow. The total flux in the air gap and the total flux in the core is the same, but the flux densities are different because the effective area of the air gap flux tube is 1.5 times larger. And so we can observe from this that we're going to have a lower air gap flux density than we are in the core. And that completes this example. Let's now consider another example where we're dealing with a motor cross-section. And in this case, I've drawn a slotless stator with a two-pole rotor. So I said it's slotless because we've got no stator teeth or stator slots. It just looks like a hollow cylinder. And then inside of our stator, our slotless stator, inside of it, we've got our two-pole rotor. So P is equal to one pole pair. And you can see that on the top of the rotor, I've put a permanent magnet with a north pole. And on the bottom, we've got a permanent magnet with a south pole facing outwards. And what we're going to do is we're going to assume that the permeability in our iron is equal to infinity in both the rotor and the stator. So that's in the iron regions. In the air gap, of course, we have a permeability of mu naught, and then our permanent magnets have whatever their permeability is of that magnetic material. Typically, it's approximately mu naught. And what I want you to do is first sketch the magnetic equivalent circuit schematic. And before you do that, let's talk a little bit about what it means that our iron permeability is infinity. So our expression for a simple flux tube is that the reluctance is equal to the length of the flux tube divided by our permeability times our cross-sectional area. And if it is that our permeability is equal to infinity, that means we have no reluctance. The reluctance is zero. And similarly, the H field in our iron region, remember, is a mathematical construct where it's equal to our physical magnetic field, B, divided by permeability, mu. And remember, since permeability is infinity, that means that our H field is zero in those regions. That does not mean that our magnetic field is zero, it just means that our H field is zero. And remember this relationship. This is going to come up, this is going to be a useful property for when we consider many different types of structures in this class. The fact that when our permeability in a region is infinity, our reluctance is zero, and our H field is zero. With that hint, please go ahead and sketch the schematic for the magnetic equivalent circuit. Please pause the video and press play when you are ready to resume. Okay, so a consequence of our permeability being infinity and our reluctance being 0 in the iron and our H field being 0 is that our entire stator is at equipotential. The magnetic voltage is the same at any point on our stator. And similarly, our entire rotor is at equipotential. It's not the same potential as the stator, but they're both at equal potential. The whole surface of the rotor is the same magnetic voltage, and the whole surface of the stator is the same magnetic voltage. So what does that mean for drawing our circuit? Let's start on the rotor. We'll put a node right here, which is our rotor. And moving from the rotor, so that would be right here, our circuit has a line going through it. Toward the stator, we have a permanent magnet, and that permanent magnet has a reluctance associated with it, and it has an MMF source. And we'll draw this in the Thevenin equivalent form. So here's the MMF, or the current linkage, the equivalent current linkage of our permanent magnet. We've got the reluctance of the permanent magnet drawn here, and next we have a reluctance associated with the air gap between the air gap and the stator. So that air gap, we have a certain length of air gap, which we call delta in this class, lowercase delta, and we have a certain height associated with our permanent magnet too. And then we have a span for our magnet, and we'll say it's equal to 90 degrees. At the end of this reluctance, we have our stator node, and so the entire stator has a single node because the whole stator surface is equal potential, has the same voltage everywhere, so it's a single node in our equivalent circuit. And moving along our stator, we are then going to have a reluctance that's through this air gap to the rotor steel. It's going to connect through here, and we'll call that reluctance R delta 0. And that connects all the way through to the rotor. And then moving further along here, we have another reluctance that goes to a permanent magnet. And this time the magnet is pushing flux towards the rotor. And then moving along here, we have yet another reluctance that goes through our air gap. And so this is our magnetic equivalent circuit for the motor. If we want to be complete, we can show this trace connecting back across. So we've got a stator node and a rotor node. And if you solve this equivalent circuit, you can again get all the fluxes through each branch. You can convert that to the fields and so on. The second part of this is I'd like you to calculate expressions for the reluctances. And we're going to do this in a similar fashion to how we did it in a previous video for calculating the reluctance of a magnet on a shaft. And that is, we'll break our magnet up into arcs of a differential thickness, which have the same angular span as our magnet. And as we know, the linear length of an angular span is going to be the following expression: the angular span times the radius. So if we set this up, we can find the reluctance of our magnet as being our length, our differential length, times our permeability of the magnet, times the radius that we're valuing the integral over, times the angular span, and finally the length into the page, where we'll integrate this from the inner radius of the magnet to the inner radius plus the length. And if you value that integral, you get this expression. Now we can do a similar thing for the reluctance that's at the surface of the magnet going out to the stator, which we just called R delta. And we can also do the same integral over this region here to get R delta 0. And this time our permeability is mu naught because we're in the air gap. Alright, so that completes this example. I have a third example that I want to briefly talk through with you. And that is, again, considering an actual motor, but this time we're going to have teeth. And pardon my drawing skills, I'm just drawing kind of an arbitrary stator here that has teeth. And I'll put a rotor in the center. And you can imagine that we can calculate all the fields in this machine using a complex magnetic equivalent circuit. So we could assign various reluctances to our stator teeth, and these would have reluctances going to the rotor. There would be a reluctance going from the rotor to the back of the stator yoke, and so on. And then in the stator yoke, you'd have some reluctance network like this. And so you can kind of get the idea here that we'd fill this whole thing up with an elaborate magnetic equivalent circuit. And if we model our windings as well, if we have a coil that wraps around this tooth, and a coil that wraps around this tooth, and so on, we would add in current linkage sources to our equivalent circuit. And so ultimately we could solve this complex set of reluctances, this reluctance network, to get our field everywhere. And depending on our rotor structure, we might have some kind of tooth shape in our rotor that as it rotates we'd be connecting and disconnecting different reluctance paths to the stator, and our various current linkage sources would be excited based on what the phase windings, the three-phase windings of the motor are doing. So this is one approach to solving for the fields in the motor, and it can be used. It's what we've been building up to. But oftentimes when we're going to be analyzing motors in this class, we're going to be taking multiple approaches, because this can be complicated, and its accuracy in some areas is very good, but its accuracy for other areas of the cross-section is limited by how much effort we put on to adding very distinct and discrete reluctances and flux tubes. So oftentimes we will take multiple approaches. We will use the magnetic equivalent circuit for some areas, a direct solution with simplifying assumptions for other areas, and field diagrams, which we haven't yet talked about, but we will be soon. And of course, finite element analysis. So it's a combination of all of these tools that we're developing that's going to enable you to effectively and quickly evaluate fields in the cross-section of your motor, which is what you're going to use to calculate the motor performance metrics. So if you want to design a good motor, you need to evaluate performance metrics, and the way that you evaluate those performance metrics is that you calculate the fields in the cross-section of your machine under different conditions. So that concludes this video. In summary, we have been tying the pieces together of magnetic equivalent circuits and showing you how you can use magnetic equivalent circuit elements within a broader reluctance network or flux tube network to solve for magnetic fields at all portions of an electric machine. We've considered both the simple transformer core example or inductor core example, as well as the cross-section of a slotless motor. And finally, we talked about how we could apply these techniques to a general slotted motor.